been on generative models and how they can be made used for making decisions. Um, at the same time, we ground these kinds of research in applications in atmospheric sciences, and this talk today is going to be about atmospheric foundation models, which sits at the very intersection of the two. So when we begin this talk, one important question to bring everyone on the same page, almost a contentious one, is what is exactly a model? So in the world of machine learning, also this definition keeps getting revisited. So when we used to call machine learning models a few years ago, the idea would be that you have some task in mind. So maybe you want to do question answering using a chatbot. You would train a machine learning model on question answer pairs. And if you've trained on enough of these pairs, the model can then be used for question answering. So this is what I refer to as the traditional machine learning paradigm. But more and more so, the world is moving to a foundation model paradigm where instead of having very task-specific models, you train a single model on large amounts of unlabeled data and very literally the entire internet and much more. And then this model has learned very general purpose capabilities that allow it to be used for any task. And that's why ChatGPT has become what it is. It's not catered to a single task. We can use it across the spectrum for any kind of language interaction. And now the question of what a model has been in the world of atmospheric sciences has largely been driven by physics. So when we think about physical models, we are thinking about systems of differential equations which govern the flow of energy and matter in the atmosphere. And this is also a groundbreaking technology, another Nobel Prize winner back in 2021, which showed how this technology has led to the whole magical world of weather forecasting, which really helps govern our day-to-day and also saves lives in so many critical sectors. This is also technology that steadily has been improving. So here on the right side, you're seeing how the technology has changed from the 1980s to where we are now in terms of the skill improving for different horizons of forecasting. So back in the 80s, we were only able to make good predictions above a certain threshold of 80% skill for 3-day predictions in the Northern Hemisphere. Now we are slowly inching towards having good predictions for up to a week for both the northern and southern hemisphere. Largely, this has been driven by the advancements in satellite technology, as well as general research in um, general research in um, is my screen visible? Yeah, in general research in how to combine all of them with first principles physics. Now, there are some key limitations of this technology, notably that it relies on physics and our physical knowledge is incomplete. It also requires access to supercomputer scale compute, which has been the luxury of only a very few organizations and labs around the world. So in that sense, it's very hard for that technology to be accessible to researchers worldwide who could then rapidly iterate over it. And lastly, even though weather and climate affect almost every aspect of our daily life, from agriculture to energy to finance, it has very limited repurposing outside of the core weather forecasting for these technologies. So it's always indirect. All these industries take the direct forecasts as one way of improving their internal workflows as opposed to directly using the physics and the uncertainty and all the everything that we know inside a physical model directly to make good use in their respective fields. On the other hand, when we talk about machine learning foundation models, think of your chat GPT. These models actually um, scale very well with both data and compute. So they don't rely on physical knowledge. They are learned in a data-driven manner. Their training can be expensive, but it's not as expensive as requiring supercomputers. So many companies and organizations around the world are now training foundation models. And importantly, so once it's trained, it's a one-time cost. When you are trying to make predictions with it, it's really fast and cheap to make predictions with these foundation models. And lastly, uh, these models are designed to be multitask in nature, so you can really adapt them to different kinds of domains very easily. And we'll see some examples of that in this talk as well. So today's talk is going to be about how do we design an atmospheric foundation model. And broadly, it will cover three major aspects. So it will cover the aspect of how do we engineer data sets, um, embrace the heterogeneity of weather and climate modeling, how do we design an objective function to train this model, and then finally, how do we adapt it to different kinds of domains. So what you would expect out of this exercise is essentially a single model which can be used for forecasting at multiple time ranges. It can be used for different kinds of spatial tasks, for example, downscaling. It can be used for regional predictions. It can be used for repurposing in various domains broadly within the field of sustainability, from agriculture to disaster management, all through a single neural network
So,
that we
yeah,
would
quick
design.
question for you. You're saying it can be used. So, is it already functional, or we
Yes.
already have
So
some?
this model is already online. It's already it's so what I'm going to talk about is a series of works. The first one in this series was Clima X, and it's open sourced. You can use it for your domain. Anybody can just download and use it. So it's already out there.
Okay, thanks.
Okay, so let's look at the different parts of this talk. So let's first start with how do we actually pre-train this model. So pre-training is the first step of any foundation model where you gather a large data set and figure out a fundamental objective that can be used for pre-training or for learning this model. So for ChatGPT, that was next token prediction, and let's see what it is for for atmospheric modeling. And I would argue that actually you can use the weather forecasting objective with a few changes, and that's good enough to define a simple and scalable objective for pre-training. So first, some really quick background on weather forecasting. So weather forecasting has a bunch of different technologies which operate. So there is, if you're looking for forecasts which are just within a few hours or less, the best thing you can do is just persistence. Whatever is the state of the atmosphere, it's not going to change much within the next hour, and that has the highest accuracy in that time range. If you go on the very extreme of trying to make predictions across of more than a few weeks or months, the best thing you can again do is just look at historical predictions and take a statistical average, and that's your climatology baseline. In the middle is where it gets interesting, which is where physics has had a big role to play, in particular through numerical weather prediction models, where the technology is basically allowing you to surpass simple statistical techniques like climatology and persistent to come up with something which actually can have much higher accuracy. So when I think about a foundation model which can operate across time and space, I'm really thinking that for a global forecast, can you actually extend this frontier using AI alone? So that would be the task we would look at as a basis for pre-training this foundation model. Now, there's broadly two worlds of forecasting that are active today. So there is an iterative forecasting approach and there is a direct forecasting approach. So let's look at direct forecasting in green here. So the task here is I have some state of the atmosphere, let's say the wind at 10 meters. That is my XT, and I'm trying to predict what would be the wind field at xt plus h. So h could be some time horizon you care about where you want to make a prediction. And one simple way of learning this mapping is just to directly train a neural network which takes xt as input and xt plus h as output. Now, this is task specific. What I mean by that is it only, for different h, you'll have to train a different model each time. But then once you have trained it for different age, it's very fast to make predictions. You just do a forward pass through a neural network and you have your model. Uh, but it also has some weaknesses, namely that it doesn't use the intermediate data really well, right? So now we have actually sensory technology which can give us forecasts at hourly or even lesser than that in some cases. Whereas here, if you're training, let's say, a model to do forecasting 7 days ahead, you're not using that data to help guide how XT should evolve to get to XT plus H. The other world of forecasting has been iterative forecasting. So here, you don't train a new model for every lead time H. You train a single model that predicts delta ahead. And if you then want to use the model to make a forecast that is more than delta ahead, let's say H, you then simply just repeat this rollout multiple times until you reach the time horizon of H. So if you're trying to make forecasts 7 days ahead and delta is, let's say, 12 hours, you would essentially run this model 14 times so that you can get a forecast at 7 days. Now, so that makes it a little slower to run, but um, what's even worse is that this can have compounding errors. So if you make a mistake for 12 hours ahead and you have to run this model multiple times, those errors can quickly compound over into giving you a very high error potentially at a longer time horizon.
Yeah, I had
And
a question.
yes.
Regarding compounding errors, typically I expect that in these kinds of situations, you tend to obtain sort of scaling limits, right? Where you have, continuous forecasting versus discrete forecasting, right? Just the way in diffusion, you typically use a continuous time, either ODE or some kind of differential equation, right? So I would like to believe that even though you have compounding errors and delta dependence, the lower the delta, somehow the lower the error I should expect, because I get closer and closer to a continuous time estimation of some sort. Does that make sense in this world?
In principle, it does, but in practice, not really, because these are all statistical models. So we wouldn't get, even if delta was really small, the error is not zero. And if you make delta really small, so let's say from 12 hours we made it to 6 hours, you have to then run the model 28 times as opposed to 14 times to get a 7-hour forecast. And the error is small, but because you have to run it more times now, that error can still compound.
Oh.
So this
Hmm.
delta then becomes a hyperparameter where if you make it too small, then the compounding happens more times, even if each time it's low, but the number of times is you have to run the model is high. And if it's too high, then you essentially in the limit just come to direct forecasting. So one has to smoothly trade off this balance in deciding what this delta is.
Okay, so
So one of
when you mean that delta is a hyperparameter, you mean that, for instance, there is no mathematical justification. It's just one of them fits the best in your situation, right?
in practice, yeah, like these are statistical models, so eventually empirical error is what would guide the best value of delta.
Okay, all right. Thank you.
Um, So one of the things we did to resolve this problem of each direct and iterative forecasting having their own pros and cons is to design a new scheme for forecasting, which has been extremely successful for us, which is to think of a new method of forecasting, which we call as RJI or randomized joint iterative forecasting. So let's unpack this. So there's essentially it's a form of iterative forecasting. Um, s- so we are predicting smaller time steps ahead, and then we will roll out until the desired lead time. But it is different from conventional iterative forecasting because of these two innovations on randomization and doing joint predictions. So what are these? So randomization means that instead of fixing a fixed delta, we actually randomize it during training of the model. So typically we would randomize it for 6 hours, 12 hours, and 24 hours. So the model is essentially tuned to learn different features at different time scales. And then to prevent this error of compounding, we not only predict what would be the forecast at xt plus delta, we also predict xt plus 2 delta, t plus 3 delta until some k, where k again could be typically like 5 to 8 is typically how we predict. So essentially the model is being told during training itself that when the model is used for test forecast, it is going to be unrolled multiple times. So in that sense, it's being learned not to just choose a setting of neural network parameters that minimize the error at t plus delta, but also a few time steps ahead. Of course, we can't make k really large, but just increasing it beyond the conventional iterative forecasting where you predict delta ahead can significantly reduce the error. So from an input-output perspective, this is the summary of what we just discussed. Direct forecasting, very simple. You have xt as input, t plus h is the output. Iterative, xt is the input. And then you also have xt plus delta for some fixed delta, which you might have as a hyperparameter. In RGI forecasting, delta also becomes an input to the model because of the randomization. And then the output is not just xt plus delta, it's the output at a few different multiples of delta as well.
So Aditya,
So
this looks like an idea which would be generic to LLMs. So does it work in other settings as well?
yeah, so all of this is assuming weather inputs and outputs, but you could apply it to any modality for any kind of time series forecasting problem in principle.
But even beyond time series, right? Well, I guess even language models would they should work, no? Or,
Yeah, in language models, if you think about this, this almost becomes like a multi-token prediction
right.
setting. And yeah, I think that's actually a very growing area in itself. Yeah. So delta can, like I said, we choose typically 6, 12, 24. 6, 12 helps learn the day-night cycle features. 24 hours helps learn more of the synoptic scale features. And like I was saying, the joint predictions over multiples of delta helps reduce the train and test mismatch, and the model consequently has less compounding errors. So does this work in practice? So first we'll see some ablations and then we'll compare against many of the other SOTA models at the time. So our model, which used many of this, we call it a stormer. So we compared the root mean squared error for different lead times. In this case, it's for temperature. And if you want more variables, those are in the paper here. And we are looking at how the root mean square error changes depending on whether you use the fixed value of delta versus whether you randomize. And you see that the errors, especially at longer lead times, are lower when you randomize the delta. The second thing was about the joint forecasting. So here again, you have to choose the value of k. So how many time steps, how many multiples of delta you predict. If you predict only one multiple, that's what you get in blue. And you can again reduce this root means this error if you predict more multiples of delta ahead. So bringing both of these together um, is what gives us the full Stormer model here. And now we are comparing it against many state-of-the-art methods. So Pangu Weather was and GraphCast, these were state-of-the-art models in 2023, published in Nature and Science. So these are what you see in blue and orange. We're looking at three variables here for a bit more comprehensiveness. There are many more in the paper. And then we're also adding more conventional baselines like persistence and climatology, as well as the physical baselines based on IFS. Um, and here again, we are seeing that Stormer um, is the only method which can extend the frontier of predictability to 2 weeks before it hits the climatology baseline, whereas other methods actually even at lower than the 2 week mark start doing worse than simple climatology. So this was very important for us to figure out how do we actually train a neural network which can serve as a foundation model for atmospheric modeling. And one of the key components here was to make it predict for multiple timescales. The second part of the talk that I want to go towards is how to think about data. So one of the things that we have embraced in this world of foundation models is to train on lots and lots of data. In fact, you can predictably say how the test loss will decrease as a function of the dataset size for neural language models. But there is some catch here. For language, we have lots and lots of data, and this experiment on the left assumes that you never see a data point again. So you have more new and new data being fed into the language model. Another work, which is where the plot on the right was from, showed that actually you can, if the data was limited, and then you would have to repeat the same copy of the data, so you'll have multiple epochs of training over the same data set. The scaling law looks a little worse. So the dotted one is what you would expect if you had no repetitions in data. But if you did have repetitions in data marked at these points, then the scaling law, the loss slope decreases much more slowly as compared to having no repetitions. So the summary of this is we need high quality, diverse data, and we don't, it's not just enough to have repeat the same high quality data. The more data sources we can find, the better we would get to what would be an idealized scaling law. So unfortunately, the world of digital data is much bigger than the world of atmospheric data. Um, and why I would claim that, even when we have access to all the satellite imagery, is that atmospheric observations, even though we have petabytes being collected every day, a lot of that is quite redundant data. In fact, I would argue that all of that data can be thought of as like videos. So you can think about temperature as a field playing over time, that's a video. Think of the diversity of that data compared to, let's say, what you would find on a medium like YouTube. Moreover, there's also challenges with how we design the architecture to ingest that data, because this data is highly multimodal. So we are not just talking about three channels, red, green, blue, like we would have in an image or in a video. We are talking about many variables and pressure levels, in addition to the fact that this data is defining a globe. So in other words, we need ways to think about how we can extend this atmospheric data and bring it to the same level of scale and diversity that we use for foundation models for vision and language. Now, just to make some of this more concrete, the most popular data that is used by the community working on AI and weather today is ERA5. It's reanalysis data from the last 4 to 5 decades, um, but it's physically constrained, right? So if you look at, it has 45 variables for at hourly intervals for, sorry, it has 45 years of data for at hourly intervals. These are how many frames you can think of, and there are around 225 variables. So if you do the math, this is about 90 million frames. YouTube, on the other hand, has 13 billion videos. So there is many orders of magnitude difference in the data sets that we are using today for AI and weather compared to what people are using for designing video foundation models. There are opportunities. So, for example, we could be looking at historical paleoclimate data, which goes even back from 1979 into much into uh, earlier decades. Or we could also be looking at future projections of the data, which is where a lot of climate modeling starts becoming relevant, of how different climate models make projections of how the state of the atmosphere will evolve over time. So we did one of these experiments where in Climate X, we combined ERA5 with CMIP data. So ERA5 is, like I said, it's only for the last 45 years, whereas CMIP6 contains uh, simulations of the climate from 1850 in the past to 2100 in the future for multiple models for different couplings and external forcings. So on one hand, we can drastically increase the volume of the data, but we need to keep in mind this is simulation data, so it might have some noise which can interfere with the training. So the real question is, how can atmospheric foundation models benefit from this diversity while keeping the signal to noise ratio in sufficiently high? So uh, we combined this data and we did this experiment where again on the x-axis you are on the y-axis you're seeing the forecasting error for 3-day prediction, and you're seeing four different variables here. So this is geopotential, temperature at two different heights, and then the U component of the wind. And on the x-axis you see the size of the data, and how we increase the size of the data was by adding more and more amounts of CMIP data. So the more amounts of CMIP data we added, and 1, 2, 3, 4, 5 is saying at each of these bubbles, this is where we added a new data set and then reevaluated the training and the benchmarking of our model. We find that as and when we increase the training data, the loss predictably goes down. In fact, the loss goes down more as the model size goes bigger. So the different shades of blue denotes transformers of increasing sizes, and the bigger models actually are more data hungry, but also overall give you lower loss. And this is a nice, easy way to increase the volume of data for training atmospheric foundation models. So another perspective to this is if you come from the world of robotics, this is what I would argue is the sim to real transfer happening for atmospheric sciences here. So that was the second component of my talk. The last one is how can we use foundation models beyond just weather forecasting? So far, uh, we have been talking about like essentially temporal predictions at multiple timescales. But the promise of foundation models is really that you can use these as substrates for anything which you think might depend on weather and climate. And this is also how the field has really been setting the bar higher and higher every year when we start thinking about generalization. So traditionally in ML, this is what I would teach is, we say that generalization is when, you have a different train and test set, and a model trained on one data subset of the data also does well on an unseen subset of the data from the same distribution. In modern machine learning, this has become a bit more richer. So we are no longer just saying that the data set is different, the task could be different as well. So if ChatGPT is trained on next token prediction, you can query it at test time to write you an email or to summarize a document, and all of those are things it would do really well on. So for the world of weather, this could mean that if you train a model to do only, let's say, medium range forecasting, can it also then be used for making good seasonal forecasts? But I would argue that broad intelligence is actually not just uh, changing the task and the data set. It should also think about modalities. Modalities could mean that if we are training a model to understand patterns in the atmosphere, that same model could then inform how would that influence the agricultural yields? How would that influence some trading strategies which are dependent on the energy and weather forecasts? So all of these tasks which do not have the same an input and output feel to it, so they don't look like a weather field, but at the same time, they do critically rely on inputs of how the forecast would change, should be innately learned by this neural network. And that's the kind of broad intelligence I hope atmospheric foundation models lead to. So we did some early work in this space. where we looked at, again, one of these models for weather forecasting. It could be the Clima X model or the Stormer models I talked about. And then we thought about how can we use this for doing climate model emulations for under different greenhouse gas forcings. So notably here, um, the inputs are greenhouse gases, like different concentrations of them. The output here are aggregate variables. So these are not the input and output variables that we had used for the weather forecasting. So at the same time, the goal was to see can the same model be fine-tuned to also understand patterns which would help with climate model emulation. Now here, one of the technical innovations in this work beyond which is goes beyond just atmospheric foundation models is how to do this fine-tuning efficiently. And this is where I'll take a small digression to talk about transformers, which is the architecture we use, and show what parts of the transformer really need fine-tuning. So this is generally the different components of a transformer. And here you have the main self-attention block, which, and this architecture, as we all know, has been the cornerstone of almost all the research happening in generative AI in the last few years. In this architecture, notably, the multi-head attention and the feed-forward layers comprise 99.9% of the parameters. So one of the things we did in an earlier work was to freeze these layers and only fine-tune the other layers for generalization across modalities. So this is what we called as the frozen pre-trained language model. And this was the first work to show that you could take a language model and generalize it to images, generalize it to DNA sequences, generalize it to solve symbolic reasoning in math, in logic. So really intelligence in a language model goes beyond just language, and it can be efficiently generalized to different modalities by fine-tuning only 0.1% of the parameters in a transformer. So we used the same insight and brought it back to atmospheric foundation models. So going back to this task where we had pre-trained a weather model, but then we wanted to change the inputs and outputs to something totally different. This is what we got the results for climate model emulations. So here we are looking at, again, the root mean square error. Lower is better for different aggregate variables, such as the surface temperatures, precipitation, and comparing against a lot of classic baselines. So this is usually a task for which there is very scarce data because climate, we don't have a lot of estimate, we don't have too much data from a time series perspective for these variables of what the climate would look like decades into the future. So typically the state of the art is from traditional baselines like random forests, Gaussian processes. Neural networks are slowly making their way into it as well. But what we showed is that actually a very large model like Clima X, and more notably its frozen variant, can actually outperform all these models through efficient fine-tuning and a pre-training phase which encompass both climate and weather data. Um, Going beyond just weather and climate, the community has now used this model for fine-tuning in so many different places. So this is an example for doing wildfire prediction and agriculture yields. People have used it for predicting damage assessments to buildings following a natural disaster. We ourselves have been using this model in collaboration with other organizations for predicting land use covers. And with Argonne National Laboratory in the US, we're using it for predicting seasonal extremes as well. So lots of different applications which indirectly depend on weather can now be enabled through a foundation model like Climax. Uh, Moving on to the last part of the talk, this is something very close to me, is which is how I think about this field and where I think it's personally headed, in especially in the context of India, is I really think about the intersection of the two as a new form of engineering science. So a lot of my research comes from a very AI first mindset, um, which often could be a bug in the sense that, maybe a lot of domain knowledge gets lost in that process. But I genuinely feel that engineering AI systems is the cleanest way to really push the boundaries of a field. And once you can engineer large scale AI systems, they will also enable the science component of it in terms of understanding of our atmosphere and improving general domain knowledge as a result. But at the same time, engineering these systems also means that we have to have a lot of high rigor in terms of how we do our benchmarking, how do we have different baselines, evaluations, and in part of that effort, my group also maintains this library called Climate Learn. It's a PyTorch-based library for doing AI and atmospheric sciences. It's open sourced, and it has a lot of these data sets, tasks, models, and evaluation in an easy to use format for the field to extend in the future. Um, we also work on releasing a lot of benchmarks. So the one I picked for this talk, which is our most recent one, it's only 2 weeks old, is IndiaWeatherBench. So the larger picture is the field has made a lot of progress for global weather forecasting. But global weather forecasting often has a limited resolution. So the best models we train today for global are around 0.25-degree resolution. Whereas when we start thinking about the impact that we can have on ground, often we might want something more higher resolution, and that often occurs in regional data sets. So these regional data sets are a big source of for improving AI systems and can have massive impact on ground. So this exercise was to work towards developing a large scale data set that the community could use at large to further progress in regional weather forecasting. Why India? Well, besides it being my home, it's also one which has very diverse climates from arid deserts to rainforests. So there's a lot of diversity of climates, which makes it a very interesting data set and benchmark uh, for furthering the science in regional weather forecasting and just the impact it can have by pushing the frontiers of weather and climate modeling on the largest population in the world. So this data set is open sourced. It's on Hugging Face. So if you have played with WeatherBench, and WeatherBench was the cornerstone of I would say almost all the progress in AI and weather forecasting at a global scale, India WeatherBench is designed to be in the same spirit, furthering progress in India and regional forecasting more broadly. So you can go to Hugging Face, download it. It's also it's how it's built under the hood is it processes the IMDA data set. So it has 57 variables across 63 pressure levels. It's very high resolution at 0.12 degrees. It contains data from the last 40 years. And the raw data is really, really big. It's many, many terabytes. So a lot of the work we did was to download the data set and make it in a more ML friendly manner. So this is how we did this, where we subsampled the data set at 6-hour intervals to reduce its redundancy in it. We looked at distinct weather variables and we put it in formats which are very easy to use for today's machine learning pipelines. Um, Along with this data set, we also trained a bunch of baselines, and that's the benchmark component of it. One of the challenges with any kind of regional modeling uh, exercise is how do we give the model additional context of what happens outside the limited geography? So this boundary can be enforced and given as in terms of what the ground truth would look like. So that's the boundary forcing approach that we benchmarked. The other one is we look at a global forecasting model and use that to infer what the boundary could look like. This is, in some sense, a more fair way of doing things. IndiaWeatherBench supports both, and you use the forecasted boundary conditions to augment your regional inputs and then predict the forecast at a future time step. We have benchmarked many of the state-of-the-art neural networks on it. This is showing you some of the results for lots of variables in the data set for different lead times and showing you how the prediction error changes when you apply these different methods on the India Weather Bench data set. Um, and yeah, I mean, there's also some case studies in case you're interested in where we try to see how different models do in predicting heat waves, which is a big extreme weather event that occurs in various parts of India every year, and how this data set enables those kinds of retroactive studies, which and the hope is as we keep pushing the models on this data set, we can actually then deploy them in production in collaboration with the Met Department of India. That I'd like to conclude and thanks all my students, particularly Tung and Jason, who led a lot of this work, and a lot of the sponsors who enabled all the experiments and resources to make this research happen. Thank you.
Thank you. Thank you, Aditya, for an excellent talk. I'll just invite some questions now.
Hi, Aditya. Very impressive talk. This is Siddharth here. I have two questions. The first one is when you showed that if you train your model with additional data, in addition to ERA 5 with SMIP models, your RMSE decreases, right? But it is also known that SMIP model has its own biases, right? So it is kind of putting a lot of data, but without any quality control. So how do you take care of that? That is my first question. And the second one is more kind of a comment than question. I would have loved to see more of the verifications on precipitation, not on temperature or winds or geopotential as such.
Yeah, so for the first question, indeed, I think ours was the first work to combine simulation data from CMIP and ERA for an AI model. And the goal of that is to actually open up more possibilities. The two for expanding that data and then doing even more quality control. So I think it's a very active area that one should, I hope the community pursues, which is we, just to give an example, we only looked at 5 CMIP data sets because of the resources constraints we had. Um, but there, as you would know, there's so many more CMIP data sets that we could look into. Now, the question also is about quality control. My personal impression is there's two axes. One is just defining a curriculum. So, for instance, curriculum could be that you first train on simulation data and then you train on reanalysis data. So, whatever the model sees more recently, that is going to influence its forecast more. So that's one way in which you can do quality control. The other is, again, taking a leaf out of the LLM playbook, which is, um, there are a lot of strategies for doing the data processing for LLMs. It's also a growing area. So deduplication, um, getting the difficulty rate or, getting additional inputs about the CMIP data set itself. So if you know about a little bit about its biases, those could be additional variables that you could augment to your data so that the model also knows what we already know could be wrong about this data. So I think that's a very, very ripe field for further exploration. Your second question was, if I understood correctly, that there are only few variables. That's only to show in the talk. I think there are about 40 variables or so if you look at the paper.
Hi, good evening. I have a small question. Can you hear
Yes.
me? Yeah, hi, I'm Venkatramana, working at the Energy and Resource Institute, New Delhi. I basically work on climate extremes. My question is regarding the RFI data. So you are feeding and training the using RFI data. Many studies, even MOU, NCMWRF and other MOS institute studies, and even I published, RFI is not capturing any extreme rainfall events. So even if you are training with that, how, what do you feel? How it good of the data set of the forecasting? And that is the first question. And what about you showed the RMSC and the other variables? How you are comparing with the forecasting with the same RFI data or some other resource?
Yeah. So about these two questions, so first question about how good is ERA5?
Yeah.
So yeah, ERA5 has its own limitations. It's a global data set. It is 0.25 degree resolution. Um, but it till date is, if you look at all the data sets in the world, which at a global level, it ranks as the most accepted data set. And it has actually been used. There are multiple studies which also show how models like GraphCast and others have used models trained on ERA5 for extreme weather prediction. So, and there's lots of case studies done by ECMWF. So, I think it's a little too extreme to say it doesn't capture any extreme weather event, but because of its limited resolution, it has its limitations in doing so. That said, so part of the exercise with releasing IndiaWeatherBench, which is actually 0.12 degrees, is to be able to capture more of these extreme weather events, which can happen at a sub-grid scale. Um, and yeah, I think so. That's where I feel like, yeah, there should be more data sets like ERA5. ERA5 will just start for that reason. Yeah, so that was one. The second question was like, how are we measuring RMSC? Yeah, we are measuring RMSC on WeatherBench, which mostly looks at ERA5 data.
Thank you. Thank you very much.
Hi Aditya, Saptarishi here. So I had a question about the fine-tuning slide that you had. So you mentioned you were using your model and then fine-tuning it for various applications like with Argon Labs and various other things. So in those projects, is it that you're showing the model newer data sets, for example, ground truth data sets for temperature and precipitation, and then just figuring out how to reduce the loss on those data sets? Like, is that the idea of all the fine-tuning applications?
Yeah, yeah. So that's how we are fine-tuning the model. And I think that's where also there is a bigger question which the language community has solved, but the vision community, which is closer to the kind of works I'm describing, has not completely solved is, can you even eliminate the need for fine-tuning? So in a lot of language applications, all you need to do for adaptability is design a new prompt. Um, but in this case is for vision, and this is also for the models we have, you need little amounts of data as well from the target application to fine-tune the models.
So just to follow up, so whatever use case that you're targeting the model to, you just take some new data set, you show the model that data, fine tune it a bit and evaluate it on that data set, and you hope to get better performance out of compared to the base model.
Yeah, and you'd evaluate it on an unseen data set from
Yeah,
the same.
unseen. Yeah.
Yeah, yeah.
And I had a second question about the GraphCast that you adapted to the IMDA through your India Weather Bench. So since GraphCast like expects kind of ERA 5 reanalysis and it's trained on ERA 5 reanalysis, did you observe any biases or issues with GraphCast when you adapted it to IMDA, or was it like did it work kind of out of the box?
So it's not the best performing model on our benchmark. And actually there, in addition to GraphCast, we also did this for Pangu Weather and Stormer. So, and because it's not the best model, I'm guessing there are some biases that it has which are affecting its performance for regional. It's a really good model, so that's why we included it, and it does fairly well in many scenarios. But I think the whole goal now is, if you have an India weather bench, let's all put our energies into beating whatever models we have. And for furthering progress in at regional timescales. So that's what I'm looking forward to, hoping the community picks it up.
Okay, thanks so much.
Yeah, one more question.
Hi, Aditya. Thanks for the talk. Very nice. I had one question about the randomized joint iteration scheme that you had. Uh, so naively, like most of these weather models, they have a kind of a curriculum setup where you first start with the easy task of predicting maybe the next state, and right, and as you go on in training, further in training, you sort of increase the lead time horizon and sort of make the task harder and harder. um, so I'm just trying to understand, because having, let's say, multiple lead times at the same time from the beginning of training, that seems to be like a harder task. So does it mean that like you had a harder time training it, or like am I missing something here? I'm
Yeah, so I think what you're suggesting is actually a really good thing one could try. So in our case, randomization was over three time steps, 6, 12, 24. So I would argue that I, I mean, I could imagine a possible extension where you try it over more time steps, which will bring its challenges and opportunities. Like challenging being that, yeah, you would need to maybe create a curriculum so that the model is not having to do very hard things all at once. But the opportunity is then maybe it makes the training even more stable. So I think actually when we have an upcoming work which looks at seasonal forecasting and pushing the state of the art there. And for those 6 hourly predictions or 12 hourly predictions are not really good tasks to give to the model. So yeah, I think there is a lot of scope there as well.
Makes sense. Thank you.
Aditya, last question. We are all very compute limited here. How much compute did you need to train your foundation model? And if you're going to compete with WeatherBench, what kind of compute do we need to have?
Yeah, very, very important question. And um, I totally relate to that in some sense. But this, yeah, while also speaking from a point of some privilege here, where at the university here we don't have too much compute either. In most US universities as well. But with partnerships, we are often able to essentially get the compute needed for early prototypes. So for instance, all the like with Argonne National Lab and Microsoft, we had access to more GPUs than we had. That said, to give you an exact number, we are not this is not like language models where it's almost impossible to train something. So here, even with, I would say like 102 H100s, you can get really far. Uh, so I think it's quite possible. And I think, I hope partnerships becomes the norm uh, everywhere, including India, where industry and public-private partnerships are more focused on AI research, and that's how I think we can do a lot through those partnerships.
Okay, yeah, this 2H100 sounds promising. uh, so any further questions? Okay. Thank you so much, Aditya. This was great. Yeah, we really appreciate your making time for us and for this informing us of so many wonderful things. Thank you.
Awesome. Thanks for having me.